In this video, we're going to take a look at circular motion. And I'm referring to it as a case study because circular motion is not a new and unique perspective, and it's really just a specific example of analyzing a particular type of interaction using multiple perspectives. Circular motion deals specifically with objects which are moving in a circle, which should be distinguished from objects which are rotating. And to help you understand what the difference is, if you take a look at a disc, and if you tied a string to that disc and you whirled it in a circle, all points of this disc are basically moving at the same speed as long as this is a long string. On the other hand, and this would be considered circular motion. Now on the other hand, when we look at rotation, what we have is every point on the object which is rotating is going about an axis of rotation which is typically inside of the object itself, although it doesn't have to be, and that all points on the object are moving at different speeds. And so this is what I mean by that. If we select a point that's located right here, then this is just a small distance, little r, from the axis of rotation. And then if you select a point out here on the edge, it's going to be a distance, capital R, from the axis of rotation. Now you know that speed is going to be equal to distance divided by time. And the distance for this rotating object, for the point on the rotating object, is going to be the circumference, which is 2 pi r, divided by the time it takes to go around. Now, because this is a rigid object, it's not a fluid of some sort, it is a disk, that means that each of these 2 points will complete a 360-degree circle or revolution in the exact same amount of time. By looking at this, we notice that the circumference, or the length of the path followed by the inner chunk of material, is going to be much smaller than the circumference followed by the chunk which is on the outside edge. And as a result, there's a small speed close to the axis of rotation and a large speed far from the axis of rotation. So this qualifies here as a rotating object based on this definition that I gave you about the points of the object having different speeds, whereas this is basically going to be considered circular motion because we can consider all of the points of the object to basically be moving with the same speed. And we're going to have a lot more to say about this whenever we study rotation, because there are some instances where circular motion and rotational motion seem to go hand in hand. You can use one or the other, but you would never be able to use both. Okay, so our chief example that demonstrates both circular motion and rotation would be the Earth. For circular motion, we have the Earth going about the Sun, but for rotation, we have the Earth going about the axis of rotation, which very nearly goes through the magnetic north and south poles, but they are not perfectly aligned. Now, circular motion basically falls into 4 different categories. Our first category for circular motion I'm going to write as HCM, which just means that we're looking at horizontal circular motion. Now, horizontal circular motion is usually going to be a uniform speed, but the actual defining characteristic is that the object is moving in a horizontal plane. That is, it's moving in a plane which is parallel to the ground, so on a tabletop, for example. And examples of horizontal circular motion would include a car making a turn, maybe spices rotating on a spice rack, and there are many others, and we're going to see lots of examples of these later on as we go through this particular part of our unit. Now, the next class of problem is going to be vertical circular motion, which I label as VCM. Now, vertical circular motion usually is non-uniform speed, because for vertical circular motion, we're looking at something like, say, a roller coaster. And if that roller coaster is going around a loop, then the roller coaster is going to start down here with a large speed, and as it goes around towards the top, it's going to slow down. And then as it comes back down from the top, it's going to speed up. And so this is a very normal thing that you've experienced a lot as you've gone to the amusement park. But the defining characteristic for vertical circular motion is that the object is moving in a vertical plane. The next class of problem that you're going to see is the frictionless banked curve, which I label as FBC. And the frictionless banked curve is usually, though it doesn't have to be, it's usually a uniform speed. And if you want to picture what a frictionless banked curve looks like, picture an icy NASCAR track. When we draw the frictionless banked curve, usually it looks like an inclined plane drawn from the side. So basically we're taking a cross section, but this turn continues to bend around into a complete circle. So you might also think of it as the sides of a wishing well. The kind where you roll the coin down into the well and it spins faster and faster as it moves towards the bottom. Now, one of the key things to remember about the frictionless banked curve is that the acceleration is parallel to the ground and not the road. And we'll see more of this again as we look individually at these various types of circular motion. Now, the frictionless banked curve is not really a particularly useful study in circular motion, with one glaring exception, in that this is the special case in order to find the critical value for a car which is going around a banked curve where friction exists. And again, we'll talk about this more later, but this is a special case. Finally, the last type of circular motion we're going to look at is orbital motion. And really, this is just an introduction to orbital mechanics. And in these types of problems, once again, we're going to be looking at a uniform speed. At least in nearly all cases. Not all necessarily, but most of them. Okay, so that's it. This was just meant to be an overview of what circular motion is and what you can expect to see in circular motion. When we talk about circular motion, basically we're talking about objects which spin around in a circle where all points of the object have the same speed, whereas with rotation, as the non-example, each point on the object is going to have a different speed as this object spins around an axis of rotation, which is typically at this located somewhere within the object and oftentimes right in the middle. So an example of a rotating object could be like a grinding wheel or the Earth rotating about its axis in 24 hours, whereas the circular motion could be understood as a car driving over the top of a hill, or the Earth going around the sun. These are all examples of circular motion. And then we have 4 classes of circular motion. And the reason that I've broken up the circular motion into 4 separate and distinct classes is just to help you to remember the specific properties whenever you see a vertical circle versus a horizontal circle. For example, in the vertical circle, you can pretty much always expect, though it's not a guarantee, you can pretty much always expect that the speed is going to be changing as you go around the circle. And with a horizontal circle, it's almost always going to be with a constant speed. That's almost always. That's not an absolute. With frictionless bank curves, it looks like a ramp and the acceleration is parallel to the ground. And so, these things are only mentioned to just help you keep track of the information and make it a little bit easier as you're studying.